recording stopped, so here we are in part 2. So the ants, no, they cannot do Pythagoras' theorem on this sphere. And in fact, it's perfectly possible on a sphere to create a triangle where the angles are all right angles. If you imagine going from the North Pole down to the equator, turning 90 degrees, going along the equator, 90 degrees to face north again, and then go back to your starting point. There you've got a triangle where the angles add up to 270 degrees. And you might be thinking, well, okay, but we don't live on a sphere. We live in a 3D space. And in this 3D space, there are some things like parallel lines. If we draw parallel lines, then they'll go on for infinity, never touching. The distance between them will always be the same. And if we measure a meter and create an object which is a meter long, no matter where we put that meter rule, it will always be a meter. And no matter how fast it's moving, it will always be a meter. Unfortunately, that's not true. The theory of relativity, which when we say theory, you've just studied science, you know that means it's true. This is something there's a lot of evidence for. Says that there is a speed limit in the universe and nothing can travel faster than that speed limit. One thing that does travel at the speed limit is light, which is why this is frequently called the speed of light. And if nothing can travel faster than the speed of light, then imagine something which is going at 3/4 of the speed of light. If they launch something at 3/4 of the speed of light, then surely it should be going at 1.5 times the speed of light. But that breaks the rules. So if the speed can't go over the limit, then something's got to give. And, well, speed is related to time and distance. So those are the things that give. Time dilation in special relativity is the concept that we experience time at different rates. Now, on Earth, the effect of this is so small that we can't really notice it. But imagine I have a twin. We start our stopwatches at the same time. Then my twin goes rapidly around the universe and then comes back. Because they have been moving faster than me, they will have experienced a different amount of time, and our stopwatches, when we put them next to each other, will say different numbers. You might be thinking, that's a great thought experiment, but it's not real. Well, it is real. GPS, the way that your phone puts a little blue dot on the map to say where you are, works by measuring the time signals to satellites. It then works out the difference in those time signals to decide where you are. And the timing needed for that is extremely precise. So the satellites that send out these time signals, they have to be corrected for relativity. And if they were not corrected for relativity, then the GPS system just wouldn't work. This is something which really does exist. Another result of relativity is that length changes. And this calculation here shows how length changes, where v is the velocity and c is the speed of light. An object which is moving incredibly quickly to an observer appears to be shorter. And so what I'm saying here really is that when we construct basic models of our universe, like this 3D space, that's not correct. That's not how our universe actually works. We don't know whether we live in a 3D space or whether we live in possibly on a 4-dimensional hypersphere. We just live on the 3-dimensional surface of that four-dimensional space. This is still something which we don't have enough evidence to say we do. We don't have enough evidence to say that we don't. It's unknown. And consequently, we can't just assume that the mathematics is correct. So what are we doing here? We're creating rules. Like in geometry, Euclid came up with rules to describe a space, like parallel lines will go on forever and not meet. 2 points can have a line drawn between them. These seem like obvious and correct rules, but we don't know. Rules like that we construct are called axioms. And just in the last 100 years or so, we've also created axioms for algebra. That first one, that a number is equal to itself, seems very obvious, but could you prove it? No, you could not. In order to prove something, you need some starting point, and then you follow some logic. And these are the starting points. The axioms are the most basic things that you can say. With the second one, A equals B means that B equals A. Well, yes, of course it does. I'm going to introduce a few more of these axioms. You don't really have to read them unless you're interested. But this is something that was introduced really by David Hilbert about 100 years ago, trying to define the rules of the game that we're doing in mathematics. And it is just that. It's a game that we're playing where we've decided the rules. And if we are thinking about this civilization on the other side of the universe, who's to say that their rules would be the same as ours? Maybe the rules that we're using are incorrect. So, final time. Decide. Would the aliens have the same mathematics as us? Okay, that's it from me. If you have any questions, please send me an email. I will try to respond to all of them and pass those out via your teachers so that you can see the responses. There's a video as well that I think you should watch, because this talk was about whether mathematics is invented or discovered, and there's a really nice TED talk on this that has lots of good examples. Like, it talks about Plato's opinion, Euclid, and so on. So that's really good for essays to have some examples and have some expert opinions on this. Okay, thanks very much. Bye-bye.